According to the National Electrical Code, lightning arrestors are required to be installed only on services supplied by overhead conductors. This requirement is found in Article 285, Section 285.26 At-1 of the National Electrical Code, which states that lightning arrestors shall be installed on each overhead service conductor entering buildings or structures. Surge suppressors, also known as transient voltage surge suppressors, are not required to be installed on all services according to the National Electrical Code. However, Article 285, Section 285.26b of the National Electrical Code states that surge suppressors shall be installed at the service entrance or other points in a distribution system where there is a risk of damage to equipment due to transient overvoltages. The function of a surge suppressor is to limit the magnitude of transient overvoltages to protect electrical equipment. Therefore, surge suppressors are recommended on all services because of the potential for voltage surges from lightning strikes or other sources to damage electrical equipment. The National Electrical Code outlines specific requirements for lightning protection systems to safeguard buildings and electrical installations from lightning strikes. Firstly, Article 250.106 addresses bonding requirements for lightning protection systems, ensuring that all non-current carrying metal parts of the system are properly bonded to the grounding electrode system. This bonding minimizes potential differences and reduces the risk of dangerous touch voltages during a lightning event. Secondly, Article 280 covers surge arrestors, which are protective devices designed to limit voltage surges caused by lightning or other transient events. These arrestors are typically installed at service entrances or other critical points in the electrical system to divert surge currents to ground, protecting sensitive equipment from damage. Thirdly, Article 285 provides comprehensive requirements for lightning protection systems, including the installation of air terminals, conductors, and grounding electrodes. It specifies the materials, dimensions, and spacing of these components to ensure effective lightning protection for buildings and structures. The article also addresses the bonding and grounding of metallic objects in the roof and within the building to minimize the risk of side flashes and step voltages. Installing surge protection devices is important to protect electronic equipment from damage caused by voltage spikes. Firstly, surge protection devices should be installed at the service entrance of the building to protect the entire electrical system from external surges. Secondly, additional surge protection devices should be installed at individual circuits or equipment to provide localized protection for sensitive electronics. Thirdly, surge protection devices should be properly grounded to ensure that surge currents are safely diverted to ground. The grounding conductor should be as short and straight as possible to minimize impedance. Lightning protection systems work by providing a low impedance path for lightning currents to flow to ground, thereby protecting the building and its contents from damage. Firstly, air terminals, also known as lightning rods, are installed on the roof of the building to intercept lightning strikes. These air terminals are typically made of copper or aluminum and are designed to provide a preferential strike point for lightning. Secondly, conductors are used to connect the air terminals to the grounding electrode system. These conductors are typically made of copper or aluminum and are sized according to the expected lightning current. Thirdly, grounding electrodes are installed in the ground to provide a low impedance path for lightning currents to dissipate into the earth. These electrodes are typically made of copper or steel and are driven deep into the ground to ensure good contact with the soil. The National Electrical Code provides guidelines for selecting the appropriate type and size of surge protection devices based on the voltage and current requirements of the electrical system. Firstly, surge protection devices are classified by their voltage protection rating, which indicates the maximum voltage that the device will allow to pass through to the protected equipment. The voltage protection rating should be selected based on the voltage level of the electrical system and the sensitivity of the protected equipment. Secondly, surge protection devices are classified by their surge current capacity, which indicates the maximum surge current that the device can withstand without failure. The surge current capacity should be selected based on the expected surge current levels in the electrical system. Thirdly, surge protection devices are available in a variety of configurations, including plug-in strips, hardwired devices, and panel-mounted devices. The configuration should be selected based on the installation requirements and the desired level of protection. Regular inspection and maintenance of lightning protection systems are essential to ensure their continued effectiveness. Firstly, air terminals should be inspected periodically to ensure that they are securely mounted and free from corrosion. Secondly, conductors should be inspected for damage or deterioration and replaced as needed. Thirdly, grounding electrodes should be tested to ensure that they provide a low impedance path to ground. The resistance to ground should be measured using a ground resistance tester and compared to the recommended values in the National Electrical Code. When installing a surge protective device, or SPD, in a panel board, several factors must be considered to ensure proper functionality and safety. Firstly, the SPD must be properly sized for the voltage and current of the electrical system. This involves selecting an SPD with a voltage rating that matches the system voltage and a surge current rating that is adequate for the expected surge events. Secondly, the SPD must be installed in accordance with the manufacturer's instructions and the National Electrical Code requirements. This includes ensuring that the SPD is properly grounded and that the connections are made with the correct torque. Thirdly, the SPD should be installed as close as possible to the equipment it is intended to protect. This minimizes the impedance of the wiring between the SPD and the equipment, which helps to reduce the voltage drop during a surge event. In addition to these considerations, it is important to select an SPD that is listed by a recognized testing laboratory such as Underwriters Laboratories to ensure that it meets safety standards. It is also important to consider the type of SPD that is appropriate for the application. There are several types of SPD available, including Type 1, Type 2, and Type 3 SPD. Type 1 SPD are typically installed at the service entrance of a building to protect the entire electrical system from external surges. Type 2 SPD are installed at distribution panels to protect downstream circuits and equipment. Type 3 SPD are installed at the point of use to protect individual devices. The NEC addresses the installation of surge protective devices in Article 242, over voltage protection. This article provides requirements for the selection, installation, and protection of SPD. It covers topics such as the location of SPD, the grounding of SPD, and the overcurrent protection of SPD. Article 242.4 requires that SPD be installed in accordance with the manufacturer's instructions. This means that the installer must carefully follow the instructions provided by the SPD manufacturer to ensure that the SPD is properly installed and will function correctly. Article 242.12 requires that SPD be grounded in accordance with Article 250. This means that the SPD must be connected to the grounding electrode system of the building. The grounding conductor must be sized in accordance with Table 250.122 and must be installed as short and straight as possible. Article 242.20 requires that SPD be protected by an overcurrent protective device, such as a circuit breaker or fuse. The overcurrent protective device must be sized to protect the SPD from damage in the event of a fault. The size of the overcurrent protective device must be determined in accordance with the manufacturer's instructions and the NEC. When selecting a surge protective device, it is important to consider the following factors. Firstly, the voltage rating of the SPD must be equal to or greater than the system voltage. Secondly, the surge current rating of the SPD must be adequate for the expected surge events. Thirdly, the SPD must be listed by a recognized testing laboratory. Fourthly, the SPD must be installed in accordance with the manufacturer's instructions and the NEC. Installing a surge protective device can help to protect your electrical system and equipment from damage caused by voltage surges. By following the requirements of the NEC and the manufacturer's instructions, you can ensure that the SPD is properly installed and will provide effective protection. The choice between a lightning arrestor and a surge suppressor depends on the specific application and the level of protection required. Lightning arrestors are designed to protect against direct lightning strikes, while surge suppressors are designed to protect against transient voltage surges caused by lightning, switching, and other sources. Lightning arrestors are typically installed at the service entrance of a building to protect the entire electrical system from direct lightning strikes. They work by diverting the high-voltage lightning current to ground, preventing it from entering the building's electrical system. Surge suppressors, on the other hand, are typically installed at distribution panels or at the point of use to protect individual circuits or equipment from transient voltage surges. They work by clamping the voltage to a safe level, preventing it from exceeding the voltage rating of the protected equipment. In general, lightning arrestors are recommended for buildings that are located in areas with a high risk of lightning strikes, while surge suppressors are recommended for all buildings to protect against transient voltage surges. In some cases, both lightning arrestors and surge suppressors may be required to provide comprehensive protection against both direct lightning strikes and transient voltage surges. Article 285 in the NEC covers lightning protection. It outlines the requirements for lightning protection systems, which are designed to protect structures and their occupants from the hazards of lightning strikes. The article covers various aspects of lightning protection, including firstly, air terminals, which are also known as lightning rods, are the components that intercept lightning strikes. The NEC specifies the materials, dimensions, and spacing of air terminals to ensure effective lightning protection. Secondly, conductors, which are used to connect the air terminals to the grounding electrode system. The NEC specifies the size and routing of conductors to provide a low impedance path for lightning currents. Thirdly, grounding electrodes are used to dissipate lightning currents into the earth. The NEC specifies the type, size, and installation of grounding electrodes to ensure effective grounding. Fourthly, bonding, which is the process of connecting metallic objects to the lightning protection system to minimize the risk of side flashes and step voltages. The NEC specifies the bonding requirements for various metallic objects such as pipes, ducts, and equipment. Fifthly, surge protection devices, or SPDs, are used to protect electrical and electronic equipment from transient voltage surges caused by lightning strikes. The NEC specifies the type, location, and installation of SPD to provide effective surge protection. The NEC provides detailed requirements for each of these components and their installation to ensure that lightning protection systems are effective and safe. It is important to consult the NEC and other relevant standards when designing and installing lightning protection systems to ensure compliance with all applicable requirements. In addition to the NEC, other standards, such as those published by the National Fire Protection Association, or NFPA, and Underwriters Laboratories, may also provide guidance on lightning protection. These standards cover various aspects of lightning protection, including risk assessment, system design, and installation practices. When designing a lightning protection system, it is important to consider the specific characteristics of the structure being protected, such as its size, shape, and location. It is also important to consider the local lightning climate, which can vary significantly from one region to another. A qualified lightning protection designer can help to assess the risks and design a system that is appropriate for the specific application. Lightning protection systems should be inspected and maintained regularly to ensure that they are in good working order. The inspection should include a visual examination of all components, as well as testing of the grounding system. Any damaged or deteriorated components should be repaired or replaced promptly. Proper lightning protection is essential for protecting structures and their occupants from the hazards of lightning strikes. By following the requirements of the NEC and other relevant standards, it is possible to design and install effective lightning protection systems that can significantly reduce the risk of lightning damage. Understanding the specific requirements outlined in Article 285 of the National Electrical Code is paramount for ensuring the safety and effectiveness of lightning protection systems. This section of the code provides comprehensive guidelines for the installation, maintenance, and inspection of these systems, which are designed to safeguard buildings and their occupants from the potentially devastating effects of lightning strikes. The NEC emphasizes the importance of using listed components in lightning protection systems. Listed components are those that have been evaluated and certified by a recognized testing laboratory, such as Underwriters Laboratories, to meet specific safety standards. Using listed components helps to ensure that the system is properly designed and installed, and that it will perform as intended in the event of a lightning strike. The NEC also requires that lightning protection systems be installed by qualified personnel. Qualified personnel are those who have the necessary training and experience to install lightning protection systems in accordance with the code. This helps to ensure that the system is installed correctly and that it will provide adequate protection. Regular inspections are essential for maintaining the effectiveness of lightning protection systems. The NEC recommends that lightning protection systems be inspected at least annually and more frequently in areas with a high risk of lightning strikes. The inspection should include a visual examination of all components, as well as testing of the grounding system. Any damaged or deteriorated components should be repaired or replaced promptly. In addition to the NEC, other standards, such as those published by the National Fire Protection Association, or NFPA, and Underwriters Laboratories, or UL, may also provide guidance on lightning protection. These standards cover various aspects of lightning protection, including risk assessment, system design, and installation practices. When designing a lightning protection system, it is important to consider the specific characteristics of the structure being protected, such as its size, shape, and location. It is also important to consider the local lightning climate, which can vary significantly from one region to another. A qualified lightning protection designer can help to assess the risks and design a system that is appropriate for the specific application. Lightning protection systems are a critical component of building safety, particularly in areas with a high risk of lightning strikes. By understanding the requirements of the NEC and other relevant standards, and by working with qualified personnel, it is possible to design and install effective lightning protection systems that can significantly reduce the risk of lightning damage.